Hi, thanks for joining this session. I'm Dr. Abdullah Mamun. I'm an assistant professor at the Nuclear Futures Institute at the Bangor University in the UK. And I'm going to talk about a new machine learning model that you have developed to automate the defects detection during additive manufacturing process. First, thanks to my collaborator, Dr. Satyajit from EDF Energy, my student Zhijin, who did most of the hard work, obviously, and Dr. Achouri, our industrial collaborator in this work. I'll take this opportunity just to introduce my institute very quickly. We are quite a new institute. So we are based in Bangor in North Wales in the UK, and we are located next to two of the best nuclear license sites in the UK, that is the Welfa and Trausfinic. And we are doing world-class research on a variety of nuclear-related topics, including nuclear materials, nuclear fuels, and nuclear structural integrity. That's our website. If you're interested, you can have a look. And the group that I'm leading, the structural integrity group, one of the main focus is to look at the structural integrity of advanced manufactured materials, that is materials by additive manufacturing or hot isostatic pressing and so on, for nuclear applications. And my today's talk is quite closely linked to this thing. So a bit of introduction. There have been quite a few good talks on additive manufacturing. Obviously, the use in nuclear throws some new challenges, the unique service conditions like irradiation, corrosion, the safety criticality, and so on. But the main barrier remains the same, that is the generation of manufacturing defects during the process. And the challenge for structural integrity is, like how to quantify these defects, how to take those into account with the structural integrity assessment, and so on. And one of the solutions that we are working towards is in situ process monitoring system for additive manufacturing system. So to give an example, so we could have multiple cameras during the manufacturing, looking at the fusion bed and monitoring any events, for example, a spark or a sharp rise of temperature and so on occurring. And if we could relate these events to the defects that occurred into our material, that can give us a very strong tools. We can improve the process, we can correlate with the process parameters, as well as it gives a lot of new opportunities. For example, all this information that we're getting for our manufactured part, we can use that for modeling the deformation. We can look at how the defects are evolving during deformation afterwards. So help with the micromechanical modeling like crystal plasticity, digital twin that some of our friends and colleagues are working for. So yeah, so it gives new opportunities as well. So obviously during additive manufacturing there could be various types of defects. For example, this unmelted particle could be due to the process parameters error, or could be due to the quality of the powders. There could be porosity for a trapped gas bubble, and there could be micro cracks. For example, it's very hard to see really. So these are very micro pores joined together. And some of these features look quite difficult to sort of distinguish even with our eyes. Like for example the unmelted particle from the porosity, and correlating these defects to the events occurring during the manufacturing process is quite a challenge. So there are the process parameters, there's the events, the defect types, and how those affect the material properties. So that's the overarching goal, to understand the relation between each of those. But in today's talk, I'll mostly focus on these machine learning algorithms which we have developed to identify different types of defects. So what we did is the material we use for this study is 316 stainless steel, which is quite widely used in nuclear applications for structural materials. And we use two different additive manufacturing techniques. One is the selective laser melting, and the other is directed energy deposition. Using these two different techniques, we have manufactured a few samples. So with the SLM, we have manufactured this cube sample, a very simple shape, and we have also manufactured these T-shaped samples, and with the DED, we have manufactured these rectangular samples. And during the manufacturing, we have varied the process parameters in a way that we have defects intentionally in our material. For example, difficult to see, but you can see in that corner that there's like a lot of large defects, so that it sort of failed that in any way. And the idea, so we have also monitored the process, with the camera during the whole process. And the idea was, like if we could correlate the process parameters, the events, and the defects that we see in our chip. And the next step, of course, was to take the samples to a metallographic preparation, which my student did, and collect a lot of images of each of the surface. And we know, like, the direction of the build of our samples, so like layer by layer we can compare which layer we have seen and spark and which layer we haven't, and so on. But for this particular machine learning algorithm, the next step was to sort of manually annotate the images. So we have identified which one is what, manually just looking at eyes, and you can see like 3 different types of defects we have identified and annotated at different colors. So red is microcracks, this one is unmelted particle or lack of fusion, and these green small dots are the various porosity. And then we mask the images with that. Okay, sorry. Okay, and then the next step was to use a set of images for each sample type, each manufacturing type, and divide it into 2 different fractions. So 70% of the images was used in training the machine learning algorithm that you have developed. And those images are augmented a few different ways. So one was resizing, so that's down to the specific model that we have used. We needed that exact resolution of the image for that. And we also did some random horizontal and vertical flips. We don't want to overtrain our model with the exact image, so so that increased the number of images we had for training as well. Okay, so I'll move on quickly. Okay, so the next critical bit is the actual development of the model. Obviously, in machine learning, which is often a combination of algorithm and maths, and it doesn't make sense all the time, But yeah, so that's why it is. But on a serious note, so our model was based on an architecture called the unit architecture. So what it does, these various steps defined here, it basically makes this very high resolution image into a lower resolution image, but keeping the high level features. So to give you an example, if you, with our human eyes, if you look at something like a beautiful mountain in Madeira, and if you focus like very small things like a house or a tree, and you try to train your mind with that's a mountain. So you'll get like 100% accuracy when you have the exact same image, exact same mountain. But if you're given a different mountain, you won't be able to say it's a mountain. So what we need is a sort of understand the neighbor of this porosity or the defects, as well as this pixelated image. And that's what it is doing. So step by step, it's just reducing down to these high level features, so where we can have this convoluted information. And the way it does is with this right hand figure, you can see. So for example, each of your pixel can have a different value, like x0, x1, x2, and they can have a different weight function. And so we want to convolute this information of all these 9 pixels into a single pixel. And the way it is done in our model is using this simple, mathematical equation, which is basically a dot product of these values of the pixel with the weight function. And I'll explain later how this weight function is being, calculated and optimized with iteration. There are a few other things in there. For example, we could use a padding, which is used for like a corner sort of pixel, so that it gets the neighboring information and so on. And of course, the stride size, you can see on this left-hand figure, how we are moving one step at a time. So this is the information of this pixel are being convoluted to, like it is the final image for this one pixel. So it's just a way of convoluting the information and having the high-level feature second. Okay, and the way it works is this. Okay, so we got our model now, which is there, and it's quite a simple algorithm where we define a certain minimum loss, and then we define the number of iteration, and it just compares this loss function with the minimum the loss with the minimum loss, and when it is smaller than the minimum loss, it just saves the model, and that's the model that we use for sort of validation and for use for our purpose. So it compares the prediction with a given sort of a test case, where we have annotated our image. Okay, so a couple of results slide. The first result slide is just on the timing and why you have used a particular types of encoder. So we have tried a few different types of encoder, VZZ11, the CNET 154 and VSET 18, and we have tried different resolution of the image as well. So it's basically a balance between the accuracy of your model and the timing, the computational time. And as you can see in these cases, we failed to identify the micro cracks, although we have identified some porosity and lack of fusion zones, where we have successfully did that within a reasonable sort of time and with a very high resolution image as well. So that just prompted us to use this particular RSNet 18 encoder. The next result slide, like how our model is doing in terms of capturing, different porosity and the lack of fusion and the micro cracks. So you can see in this bar chart on the overall defect side, it has a very good accuracy of almost like 90%, over 90%. So out of, I think, sorry, it is quite small, but the green one is the test case, and this light green one is the prediction of the model. So out of 700, it has captured almost like 650 defects. So if you look at separately for lack of fusion zone, it has over-predicted by 15%. For porosity, it has under-predicted by 8%. And for microcracks, it didn't do very well. So it has over-predicted by about 62%. So probably this doesn't tell the full story because, yeah, so it just tells you the number. But a better way to look at it is using this confusion matrix, where you can see this. So this is the prediction, and this is the actual data. So out of 143, it has predicted the 148 of this lack of fusion, but it also characterized 23 of the porosity as lack of fusion zone. And for porosity, it did much better, but it has characterized another 8 microcracks as porosity and so on. But for microcrack, it did much worse. I think one of my last slide is, so the other important information we are interested in, not only on the numbers of different defects, but also like their location and their size. So, and the way we have sort of characterized it is using this function where it's division of the area of overlap with the area of union. So it's a common way to sort of characterize. So you can see that in some cases it didn't predict the right size of the crack. For example, there is a predicted shorter cracks. In some cases it predicted an extra sort of porosity, and in some cases it hasn't predicted a micro crack, and so on. I'll skip this slide. So that brings to the summary of this work. So we had developed this new machine learning model which quite accurately classify and identify the porosity and the lack of fusion zone in additive manufactured part. And that's the first step of the whole package that we are doing. So the next step is to correlate this with the events that we have captured using our camera. And also we are working on improving the monitoring system as well as the improving our model as well. So that's me. Thank you.
Thank you for the nice presentation. Is there any question from the audience? Please.
Thanks for your presentation, very interesting. My question is about the classification. So how do you discriminate between lack of fusion defects and cracks? Because I mean, if you look at across the building direction, then lack of fusion might appear as pores defect. But if you look at the transverse direction, they might appear like cracks.
Yeah.
So what?
Yeah, that's a very good question. So at the moment, we are only limited to a 2D surface. So that's what we are looking at, just a 2D surface along the building direction. And we are missing out on this information. So at the moment, there is no way for us to look at the 3D information. But one of the things we are trying to do is using an XCT, computer tomography technique to sort of capture the 3D version of these various defects. So that will give us that information. At the moment, we are just whatever appears on the surface with our eyes, that's what we are characterizing as porosity.
So you're saying that some of those cracks that you detect might be lack of
yes,
fusion?
It could be. Yes, it could be. Yes.
All right, thank you. Thank you very much.
Any other question? No? I think we can proceed.
Yes.
Thank you again.